Welcome to another filament testing video. This is Bambu Lab PPS-CF, and this box is sent to me by Bambu Lab in exchange for the review. There is no additional payment, but this video and the whole channel is sponsored by Polymaker. Few specifications from the website. Immediately a warning that it can be printed only on X1E or H2 printers from the Bambu Lab offer. Ultra high heat resistance, and probably my temperature test will be completely useless here because I will reach the maximal temperature of my equipment of approximately 230 degrees Celsius, and it will not even be close to those 260 something according to specifications. Great mechanical properties, this is what I am testing. And solvent and chemical resistant, extremely chemical resistant material, and this is something I'm not testing, but if you need this property, definitely this is a great material, much better even compared to the PPA, for example, CF, which I already tested. It is very strong material, but this has better chemical resistance. Ultra low water absorption. AMS not compatible. 0.4mm or bigger nozzle, they recommend 0.6, but I will print everything with 0.4mm, and it has very typical metallic sound. Now the print temperatures. The nozzle between 310 and 340 degrees Celsius, but of course I will use the default settings in the Bambu Studio. On the bed between 100 and 120 degrees Celsius with the glue. And I will test it on H2S printer, and unfortunately I have only textured PI sheet. I know the smooth would be better here, and I hope the glue will be enough and I will have good bed adhesion. Let's see what's in the box. Nice vacuum packaging, a sticker with recommended print temperatures, same like already mentioned. Looks like the bag is not resealable. It arrives on this cardboard spool, which is good for the drying. I think if it is the same like a PPA, then it can withstand the temperature up to 140 degrees Celsius, and they recommend the drying on 120 few hours. And the filament is glued, but let's see how brittle is this filament. Okay, let's measure it. Start angle 30 degrees. Around 70. It's close to the brittle category, but still acceptable. One more time. The oven is preheated to 120 degrees Celsius, and I'm controlling the temperature with additional thermometer. And it will be dry together with the PPA-CF because I need some test objects from this filament too. If I will measure their weight every half hours, in that case I can calculate how much moisture they had in them. I can measure changes in both filaments, but definitely more in the PPA, which is nylon, even if it is stored in the vacuum. Depends on the targeted moisture, but PPS was ready for the printing even after 2 hours of drying. PPA was still not. Quickly to check how brittle is the filament after the drying. Start angle 30 degrees. Very similar. These are the measure points, and in infinity it will become a constant, and that can be calculated. And there's a theoretical dry mass, and from this I calculated that I stopped the drying at 0.09% of the moisture, but even out of the box with 0.36 it will be completely fine. Same calculation for PPA-CF, it started from 1.75 and ended with 0.68% of the moisture after 4 hours of drying. You can see the printings in my H2S review video. The printing will be on H2S with actively heated chamber of 65 degrees Celsius, 320 on the nozzle, and 60 will be the maximal flow rate, and here you can see the part cooling. These are my regular test objects. Since it cannot go into the AMS, I'm using the external spool holder. I'm using the glue stick, and doors will be closed. And it started, but not easy to watch because black filament inside the enclosure. Let's check the camera from the printer. Well, better than looking from outside. It just started with the 4th layer and the temperature is stable 65 degrees Celsius inside. The printing is at 60%, not super fast printing, but very nice. In 4 minutes printing will be finished. Quick bed adhesion check. Oh, it's good, but okay, it's acceptable. Definitely I like better the smooth sheet. And as always with the PPS reviews, a bell. finish. I'm reprinting the layer adhesion test objects on 340 degrees Celsius because I experienced that some materials require this temperature. Next to it I'm printing the corner bracket, so it will be not completely a fair comparison, but hey, sometimes we don't have a choice. Tensile test with horizontally printed test objects. Very strong. For better comparison, I will include the data for Bambu Lab PPA-CF from earlier video, which is still the strongest filament type I ever tested. But this is very strong too, and I don't want you to get the wrong picture about PPS-CF, so I include the data here for the average ABS. And here you can see actually how strong is this filament. Layer adhesion vertical test objects, default settings. Layer adhesion printed on 340 degrees Celsius. Noticeably stronger. Here you can see my rating for the layer adhesion for this test object, and we can see PPS-CF printed on default settings is quite weak. But I believe that they advise this 320 degrees Celsius because of their X1E, because this is the maximum temperature for it. But look at this, printed on 340 degrees Celsius, the improvement is very noticeable, and I believe that we can go even higher, so definitely I would recommend you to try 350 degrees Celsius, and the layer adhesion will be somewhere between acceptable and good. Shear test side by side, horizontally and vertically printed test objects. Yes, compared to the PPA, this filament is weaker, but look at this, it is very rare that I have to use that stronger crane scale because my main scale can measure up to 200 kilograms. So this is very strong too, printed in horizontal position. Printed vertically, we have that weakness of the layer adhesion. Let's say this is still acceptable. Torsion test side by side, horizontal and vertical objects. 1.2. 1. This one printed in vertical position breaks very suddenly, no surprises here. But this printed in horizontal position break on quite low load, and this is because of this weaker layer and wall adhesion. I'm not sure if you can see this on the screen too. Definitely with the better layer adhesion, this would break on much higher load. Unfortunately in this test, even if printed in horizontal position, it was quite weak because of that layer and wall adhesion. 3-point bending test, distance between supports is 50 mm, and I'm placing these loads one by one and measuring the deformation after 1, 30 and 60 seconds. The load is 2.5 kilograms. This is the deformation under 5 kilograms and under 10 kilograms. With removed load, almost zero deformation. In this test, yes, it has more deformation compared to the PPA-CF, but even then this is very strong and stiff material, and look at this, no additional deformation during the time, even under 10 kilograms. Impact test with this 10 kilogram hammer. 0 position. Distance from the 0 position is 47 mm, and from this I can calculate the breaking energy. Both materials are very similar in this test. They are more brittle compared to the average ABS, but still tougher compared to the average PLA. Creep test the deformation under constant load of 1.25 kilograms. $12.49. The deformation is so small that I have to go around. Too small gap for the bolt. This is the last day of the measuring, and I already know the result because even compared to the day 0, there was absolutely no changes. Let me show it to you. 12.50. Visually no deformation on it at all. On this graph you can see the directly measured values, distance between two reference surfaces, and yes, we can see more deformation on a PPS-CF, but the creeping is the difference between 2 days, which is basically zero almost in both cases, because these are very stiff, rigid materials and resist good to the creeping. And now that bracket test from my PET-CF comparison video, and this time I'm using the torque wrench set to 1 Nm. The load will be 2.5 kilograms on exactly 200 mm distance, and deformation is slightly smaller compared to the average PET-CF. In that video I included this aluminum bracket, but it has only one bolt for each side. In the meantime, this one arrived still from aluminum, and it is better, but interesting, not so good as 3D printed versions. Still not fair comparison, because 3D printed bracket has the supports from two sides, and this one only on one, and it is thinner. But it is good to be familiar with the possibilities. Another great example for the practical application. On my workplace we have a spray dryer, and this part which connects the bottle broke, and the replacement part cost us more than $200 together with the shipping, and the only reason why it is so expensive that it can withstand these higher temperatures, which is basically nothing for this PPS material. And I'm working on the project, so it will be replaced with the 3D printed part. Summary of all results on one place, and this one line will be added to the summary table for my Patreon supporters. Result for the shear test, bending test, deformation after 30 seconds, bending test, deformation after 1, 30 and 60 seconds, torsion test, impact test, and result of my drawing for PPS-CF and PPA-CF. Watching the mechanical properties, maybe it's not the best comparison with PPA-CF. Maybe with the PET-CF would be more reasonable, but you can watch that video, or my Patreon supporters can do this comparison with just few clicks. But anyway, PPS-CF is still very strong material compared to the regular ABS. And if you need a great chemical and temperature resistance, then this is fantastic material. Only don't forget that you need a printer which is able to print on these higher temperatures. This is my experience with the PPS-CF from the Bambu Lab. If you have some other experience suggestions, then few lines down in the comment section. Thank you for watching and happy printing!